Welcome. Today we are going to discuss the third module of fourth chapter. In this module, we shall introduce the concept of line integrals. Since the concept is a new one for us, we shall discuss several examples. In the previous module, we made a detailed discussion regarding curves and arc lengths of rectifiable curves. This module is dedicated towards discussing line integrals. First of all, we introduce line integrals. Line integral. Let gamma from AB to Rn be a piecewise smooth curve. Capital A is an open set in Rn containing the trace of the curve gamma, and f from A to Rn be a bounded function. The line integral of f along gamma is denoted by integral inner product f d gamma and is defined by integral inner product f d gamma equal to integration a to b inner product f gamma t gamma dash t dt, provided the integral in the right hand side exists. We even don't bother if it exists as an improper integral. In the above definition, by inner product we mean the standard inner product on Rn. Now, here f gamma t is a point in Rn and gamma dash t is also a point in Rn. Thus, inner product of f gamma t and gamma dash t is a well-defined real number. Thus, we can treat integral f d gamma as an Riemann integral where the integrand is inner product f gamma t and gamma dash t, and we are integrating this with respect to t, the limits of the integral being a and b. We cite an example. Example 1. Let a be positive. We try to evaluate the line integral f d gamma where f from R2 to R2 is defined by fxy equal to y 2a minus x for every xy, and the path gamma from 0 to 2 pi to R2 is defined by gamma t is a times 1 minus cos t, a times t minus sin t for every t in 0 to 2 pi. We have given a graph of this curve. Now, for every t in 0 to 2 pi, gamma t equals a times 1 minus cos t, a times t minus sin t. Differentiating with respect to t, we find gamma dash t equal to a sin t, a minus a cos t. Also, f gamma t equal to f evaluated at the point a times 1 minus cos t, a t minus sin t. So, it equals with a t minus a sin t, comma a plus a cos t. Consequently, we calculate the inner product of f gamma t and gamma dash t, and we find it is a square t sin t. Therefore, line integral f d gamma equals integral 0 to 2 pi a square t sin t dt. Using integration by parts, we find integral t sin t dt equal to minus t cos t plus sin t. Therefore, line integral f d gamma equals minus 2 pi a square. In this problem, the curve was given in a parameterized form. In some cases, we are given the curve and we have to find parameters for it. The next example, let a and b be both positive. We have to evaluate the line integral for the vector field f from R2 to R2 defined by fxy equals ordered pair px plus qy and px minus qy for every xy in R2, and the curve is the ellipse x square by a square plus y square by b square equals to 1 rounded once in the anticlockwise direction. Here p and q are two arbitrary constants. So, we have shown here the curve. Now, we can parameterize the given curve as gamma t equals to a cos t b sin t, that is x t is a cos t and y t is b sin t for every t coming from 0 to 2 pi. Then for every t in this bounded closed interval, gamma dash t equals ordered pair minus a sin t b cos t. Accordingly, the curve under consideration is smooth. Now for every such t, f of gamma t equals pa cos t plus qb sin t, pa cos t minus qb sin t. As a result, the inner product of f gamma t and gamma dash t is PAB cosine square t minus QAB sin square t minus PA square plus QB square sin t cos t. Calculating, we find line integral f d gamma equal to integral 0 to 2 pi inner product f gamma t gamma dash t dt, and which equals with p minus q ab pi. We have shown here the calculations. One remark at this point. An inquisitive reader may doubt whether all the parameterizations would yield the same result. After a few steps, we shall show that a line integral remains unaltered under change of parameter, provided the orientation of the curve remains the same. Now, let gamma be a smooth curve defined over Rm, and the domain of the function gamma is bounded closed interval a to b. A is an open set in Rn containing the trace of gamma, and F is a vector field in Rm defined over A. If we express both f and gamma in terms of their component functions, that is, if we express f as ordered m-tuple f1, f2 up to fn and gamma as gamma 1, gamma 2, gamma m, then we have the following. Inner product of f gamma t and gamma dash t equal to inner product of the m vectors f1 gamma t, f2 gamma t up to fm gamma t with gamma 1 dash t, gamma 2 dash t up to gamma m dash t, which equals summation from k to m fk gamma t, gamma k dash t. As a result, we can check line integral a to b f d gamma equals with integral a to b summation k equal to 1 to m fk gamma t, gamma k dash t dt. Here the summation and integration change their place. So, we have summation k equal to 1 to m integral over a to b f k d gamma k. Thus, we can write integral a to b f d gamma line integral equals integral a to b f1 d gamma 1 summation continued up to a to b fm d gamma m. We notice here that f1 up to fm and gamma 1 up to fm all are real valued functions. So, their usual product coincides with their inner product. We cite an example here. Let C be the circle given by x square plus y square equal to a square, where a is a positive number, and we consider the line integral over C x minus y dx plus x plus y dy divided by x square plus y square square. So, we want to write down it in the above form. So, the integrand is found to be fxy equal to ordered pair f1 xy, f2 xy, where f1 xy equals x minus y divided by x square plus y square whole square, and f2 xy equal to x plus y divided by x square plus y square whole square. Clearly, f is a function defined over R2 except the origin. Here we have shown the curve over which we are going to find the line integral. Now, a parametric form of the circle is given by x equal to a cosine t, y equal to a sine t. So, we now use the previous result we deduced, and we find that the value of the line integral equals integral over c x minus y x square plus y square whole square dx plus integral over c x plus y by x square plus y square whole square dy. We put here x equal to a cosine t and y equal to a sine t, and ultimately we find the value of the line integral as 2 pi. Another example. We consider the vector field f defined over R2 as follows. Fxy equals x plus root y, x minus root y for every ordered pair xy where y is non-negative. And also we are considering the non-negative square root only. We find the line integral of f from the origin to the point 1, 1, but along two different curves. First, along the line segment joining the points 0, 0 and 1, 1, and then along the curve alpha defined by alpha t equal to t cube t square. First, let gamma be the straight line segment joining the points 0, 0 and 1, 1 in R2. So, we can express gamma t equal to ordered pair Tt. So, we can check both the curves gamma and alpha are smooth. We have shown here the curves gamma in the left and the curve alpha in the right. Now we find that inner product of f gamma dash t equals to 2t. Therefore, line integral 0 to 1 f d gamma equals with 1. And similarly for the curve alpha we find inner product of f alpha dash t equals with 3t to the power 5 plus 2t to the power 4 plus 3t cube minus 2t square. Hence we find that the value of the line integral 0 to 1 f d gamma equals with 59 by 60. That is, for different paths we find different values of the line integral. Thus, this example shows that the value of a line integral, if exists, depends not only the initial and terminal points of the curve only, but on the path joining them also. Now, it is time to discuss some fundamental properties of line integral. First result, line integral is linear with respect to the integrand. That is, let gamma from bounded closed interval a b to Rn be a piecewise smooth curve and fg are two functions defined over a set A such that both the line integrals a to b f d gamma and a to b g d gamma exist. Here we assume that trace gamma is a subset of A. Then for every pair of real numbers lambda and mu, line integral a to b lambda f plus mu g d gamma exists, and moreover line integral a to b lambda f plus mu g d gamma equals with lambda times integral a to b f d gamma plus mu times integral a to b g d gamma. First we find that the inner product of lambda f plus mu g gamma t and gamma dash t equals with lambda times f gamma dash t plus mu times g gamma dash t using the linearity property of inner product. Now it is given that both the line integrals integral a to b f d gamma and integral a to b g d gamma exist. From this we have proved the result. The calculations are shown here. Now we define join of two curves. Let gamma 1 from AB to Rn and gamma 2 from BC to Rn be two curves satisfying gamma 1b equals to gamma 2b. That is, the terminal point of the first curve coincides with the initial point of the second curve. We define a new curve gamma from AC to Rn as follows. Gamma t is gamma 1t if t is from AB and equals with gamma 2t if t is from BC. Clearly, the continuity of gamma at any point in AC except the point V follows from the continuities of gamma 1 and gamma 2, and its continuity at the point C follows from the Pesting lemma. Thus, gamma is a curve in Rn. We call it the join of gamma 1 and gamma 2, and usually we denote this by writing gamma equal to gamma 1 plus gamma 2. We have to take care of two things. First, we can join finitely many curves in this manner, and secondly, this join is associative. Now a result. Let gamma 1 from AB to Rn and gamma 2 from BC to Rn be two piecewise smooth curves, and gamma is the join of gamma 1 and gamma 2. Let A be an open set in Rn containing the trace of gamma, and f from A to Rn be a bounded function such that both the line integrals integral a to b f d gamma 1 and integral b to c f d gamma 2 exist. We claim that integral a to c f d gamma exists, and value of this line integral equals with the sum of the line integrals a to b f d gamma 1 and b to c f d gamma 2. Now, from the given condition, we find that integral over a to c f d gamma, first we write down following the definition, then we write it as the sum of two integrals by breaking the domain, and finally we find that this equals with integral a to b f d gamma 1 added with the line integral b to c f d gamma 2. Now, another example. Let a be a positive number. We have to calculate the line integral over gamma dx plus dy by mod x plus mod y. Clearly, here the function 1 upon mod x plus mod y is defined everywhere in R2 except at the points where both x and y are 0, that is except at the origin. And gamma is the square with vertices a 0 minus a, b a 0, c 0a and d minus a 0 traversed once in the counterclockwise directions. That means it ends the journey by coming to the starting point, but we can consider the starting point as an arbitrary point. So, we can write gamma equal to gamma 1 plus gamma 2 plus gamma 3 plus gamma 4, where gamma 1, gamma 2, gamma 3, gamma 4 denote respectively the line segments AB, BC, CD and DA. We have shown the curve here. First step is we parameterize all the 4 curves one by one. We have shown the parameterizations here. Here the integrand is a vector field defined over the punctured R2 as fxy equal to 1 upon mod x y, 1 upon mod x plus mod y for every possible xy. Now, the curve gamma 1 lies in the 4th quadrant. So, for this the first coordinate is non-negative and the second coordinate is non-positive. Keeping that in mind, we find that for points on gamma fxy is nothing but ordered pair 1 upon a, 1 upon a. Consequently, we find that the value of line integral over gamma 1 f d gamma 1 equals 2. In a similar process, we find integral over gamma 2 f d gamma 2 0, line integral over gamma 3 f d gamma 3 equal to minus 2, and line integral over gamma 4 f d gamma 4 equals 0. So, we use the previous result and find after adding all these 4 relations integral over gamma f d gamma equals 0. Till now, we have solved many problems. In some of these problems, the curve was given to us with some orientation, and we have to find some parametric representation of the given curve. Now, suppose I solve a problem with one parameterization, but another one solves with another. So, where is the guarantee that we would yield the same result? Now, we show that the value of a line integral remains same with reparameterization provided we do not change the orientation of the curve. In the earlier module, we discussed reparameterization in detail. Let gamma from AB to Rn be a smooth curve and h from CD to AB, both are bounded closed intervals, be a continuous function. Then beta equal to gamma compose h from CD to Rn is another curve in Rn. We called beta a reparameterization of gamma by h. H is called the change of parameter function in this case. Unless otherwise mentioned, in the remaining portion of this chapter, we shall assume that the change of parameter function h satisfies the following two conditions. First one, H from CD to AB is bijective. Secondly, H is continuously differentiable over CD with non-vanishing derivative, that is H dash S not equal to 0 for every S from bounded closed interval CD. We shall show that this kind of change of parameter functions induce an equivalence relation, say tilde, over all smooth curves in Rn sharing the same trace. We define gamma has the relation with alpha if and only if alpha is such a reparameterization for gamma. Let gamma from AB to Rn be an arbitrary smooth curve. The identity map I from AB to AB satisfies both the above conditions mentioned above. I is bijective and the derivative of I is 1, which is non-zero everywhere. Since gamma is gamma composition I, it follows that gamma has this relation with gamma. Since gamma was an arbitrarily chosen smooth curve in Rn, it follows that the relation is reflexive. Next, let alpha and gamma be two curves in Rn where gamma has this relation with alpha. Then there exists a map H from CD to AB such that H is bijective and continuously differentiable with nowhere vanishing derivative, where alpha equals gamma compose H. Now, by inverse function theorem, H inverse exists, it is continuously differentiable, and for every S from CD, H inverse dash at the point Hs equals with 1 upon H dash S. H dash S is non-vanishing and hence H inverse dash H is also. Thus, H inverse also satisfies the required two conditions and gamma equal to alpha compose H inverse. Consequently, alpha has this relation with gamma. Therefore, the relation under consideration is symmetric also. Finally, let gamma has this relation with alpha and alpha share the relation with beta. Then there exists two continuously differentiable bijective function h1, h2 with nowhere vanishing derivative and alpha equal to gamma compose h1, beta equal to alpha compose h2. Let h equal to h1 compose h2. Then beta equals gamma compose h. Since the composition of two bijective functions is bijective, h is bijective also. Chain rule assists us to convince that h is also continuously differentiable and h dash vanishes nowhere in our scope of discussion. As a result, gamma has this relation with beta. Thus, the relation is transitive and hence is an equivalence relation. Now, we discuss a result. Let gamma and alpha be two equivalent smooth curves in Rn and f is a bounded function defined over an open set containing the trace of these two curves. We note that gamma and alpha share the common trace. If the change of parameter function h is continuously differentiable and orientation preserving, then line integral fd gamma equals with line integral fd alpha. We give the proof. Given gamma from AB to Rn be a smooth curve and h from CD to AB is bijective continuously differentiable function with nowhere vanishing derivative and alpha equal to gamma compose h. By chain rule, for every S in CD, we find that alpha dash S equals with gamma compose H dash S, that is gamma dash HS H dash S, which equals with gamma dash T H dash S, where T is HS. So, for S in CD, we can write inner product F alpha S alpha dash S equals F gamma T gamma dash T H dash S. Now, H dash S is a real number. F gamma T and gamma dash T both are members in Rn, that is the vectors. So, we can write this as H dash S inner product F gamma T gamma dash T using the homogeneity property of inner product. Therefore, integral C to D inner product F alpha S alpha dash S ds equals with C2D H dash S inner product F gamma T gamma dash T. This equals from Hc to Hd inner product F gamma T gamma dash T dt. Here we substitute T for S and that equals with integral A to B F gamma T gamma dash T dt. Now since H is orientation preserving, we have Hc equals A and Hd equal to B. So the result follows. In contrary to the above, if alpha would be an orientation reversing reparameterization of gamma, then the proof would involve similar steps. There would be no change in the integrand, only at the last step. While we are substituting T for S, we find integral C to D inner product F alpha S alpha dash S ds equals Hc to Hd inner product F gamma T gamma dash T dt. This equals integral B to A, not A to B, inner product F gamma T gamma dash T dt, and this equals with negative of integral A to B F gamma T gamma dash T dt. Thus, the value of the line integral would be the same with a change in sign. One remark here, in case we consider gamma a piecewise smooth curve, we can arrive at similar steps as shown above. The only difference is that we would perform the same steps for each piece in which the curve is smooth. That is, the above result can be extended for piecewise smooth curves also. Now one result which we usually call the ML formula. Let gamma from AB to Rn be a piecewise smooth curve. A is an open set in Rn containing the trace of the curve gamma, and F from A to Rn be a bounded function. Let the arc length of gamma be L and capital M be an upper bound for norm F in A, that is upper bound of norm Ft for every t in A. Then we observe that line integral of f d gamma equals with integral A to B inner product f gamma t gamma dash t dt. Now we know that for every t, inner product f gamma t gamma dash t is a real number which is less than or equal to modulus of f gamma t gamma dash t. So using a property of Riemann integration, we find that this is less or equal to integral A to B modulus inner product f gamma t gamma dash t dt. Now we use Cauchy-Schwarz inequality and we find that this is less or equal to integral A to B norm of f gamma t norm of gamma dash t dt. Now for every t, norm of f gamma t is less or equal to m. We use the property of Riemann integration and find that it is less or equal to m times integral A to B norm gamma dash t dt. We know integral A to B norm gamma dash t dt is nothing but length of the curve gamma, so which equals with L. So this equals with ml. This gives an upper bound of a line integral. Now line integral with respect to arc length parameter. Let gamma from AB to Rn be a smooth curve. Then the arc length of gamma is given by St equals with integral A to t norm of gamma dash u du. We know S is differentiable and for every t, S dash t is nothing but norm of gamma dash t. Now let f be a bounded function defined over set A, where A is an open set in Rn containing the trace of gamma. We define a scalar field capital F on the trace of gamma as follows: f of gamma t equal to inner product f gamma t gamma dash t by norm of gamma dash t for every t in AB. That is, we take the inner product of f gamma t with the unit tangent at the point t on the curve gamma. Then f gamma t s dash t equals with inner product f gamma t gamma dash t. Therefore, integral over A to B f gamma t s dash t dt equals with line integral f d gamma. We can write ds for s dash t dt and change the limits of integration accordingly. This motivates us to define the line integral of a scalar field defined on the trace of a rectifiable curve with respect to the arc length parameter as follows. Let capital F be a scalar field defined on the trace of a rectifiable curve gamma, and let S denote the arc length function of gamma starting from a suitable point. Then we find that integral over gamma capital F ds equals integral a to b f gamma t s dash t dt. Thus, in this module, we introduced line integrals, studied some properties of line integrals, and have shown how to solve problems with line integrals. The study of line integrals will be continued in the next module also.